Thus far, we've talked about several ways to solve differential equations of first order. This video is going to take a look at equations that are close to a method we know how to solve and how we can do a substitution to make them into a nicer format. Our question is going to be, how do we transform a differential equation into a solvable form? And there's two types we're going to look at as we do this. The first type is what are called homogeneous. And a homogeneous equation is of the form f of x comma y dx plus g of x comma y dy. And the way that we are going to identify it as a homogeneous equation is we're going to calculate f of xt comma yt. And we want it to equal t to some exponent times the original function f of y. And in fact, we're going to have to do this on both parts. So we're going to replace all the x's with xt and the y's with yt and g as well, and see if we can pull out a t to the alpha times g of xy. If we can do this, where we have the same exponent on both parts, it is a homogeneous first-ordered differential equation, and we can solve it by doing one of two very similar substitutions. We can either let the y equal a u times x, or we can let the x equal u times y. Either way works, and when we do that, we're also going to calculate dy, which is the derivative of the product. Using the product rule, we have x du plus u dx, or on the other one, dx would be y du plus u dy. And when we do that substitution, it might get ugly on the algebra for a minute, but after we fix the algebra, then it becomes a separable equation every time. So let's try an example where we do just that. Let's solve x squared plus y squared dx plus x squared minus xy dy equals 0. Now, first we have to determine, is it homogeneous? And the way we do that is we replace the x with xt squared plus, and replace the y with yt squared, and see if we can pull out the t's to get the original expression. Well, sure enough, here we get x squared t squared plus y squared t squared. Factor out the t squared, and we get the original function x squared plus y squared. That's a good sign, but it has to work on both sides. So let's try that. Xt squared minus, replace the x with xt, replace the y with yt, and we get x squared t squared minus t squared xy. And sure enough, we can pull out the t squared, which leaves behind x squared minus xy, the original expression. So sure enough, it works. We have a homogeneous first-ordered differential equation. We can now make a substitution in order to make it into a separable. We can use either y equals ux or x equals uy. Both will work. Both give you the same result. In this case, neither one is necessarily easier or more simple or complex. So let's just do the y equals ux. And then dy is going to become x du plus u dx from the chain rule. And then we can take our original function and make that substitution, and it should be a separable equation. But let's get some more space to do that. Okay, so we have x squared plus y, which is ux squared dx, plus x squared minus xy, which is ux, dy, which now becomes x du plus u dx, and the whole thing equals 0. Now what we're going to do here is we're going to multiply this out as much as we can so we can separate the du's from the dx's. We'll do a little simplifying as we go. So we've got x squared dx plus, I'm going to call that u squared x squared dx, plus we end up with an x cubed du plus an x squared u dx minus, we got 3 x's, so that's x cubed u du minus x squared u squared dx equals 0. Okay, what I'm going to do then here is we're going to separate all the dx's. We'll keep them on the left side, and we're going to move all the du's over to the other side, because we're working on making it a separable equation. So we have x squared plus u squared x squared plus x squared u minus x squared u squared, all with the dx's, is equal to, coming onto the other side is all the du's, and x cubed u minus x cubed du. And now it's clearly separable if we factor out the x squared, leaving behind, and actually as I look inside here, we've got an x squared u squared minus x squared u squared. Those all go to 0, which is nice. So we have x squared times 1 plus u dx is equal to, factoring out the x cubed, u minus 1 du. Dividing to get the correct separation of variables. When we divide by x cubed, we get 1 over x dx is equal to u minus 1 over 1 plus u du. Finally, we've separated. We're ready to integrate both sides. But before we do, I'm going to do some long division on that fraction to make it easier to integrate. I'm going to take u plus 1 and divide it into u minus 1, which goes in there once, gives us a negative u and a negative 1. So we have a negative 2 remainder, so that's negative 2 over u plus 1. That's going to be easier to integrate. So we actually have 1 over x dx is equal to 1 minus 2 over u plus 1 du. All right, let's scroll down again and integrate both sides to get the natural log of x is equal to u minus 2 natural log of u plus 1 plus our constant. And we're almost there. If we scroll up, remember we said originally we let y equal ux, which means if I solve that for u is equal to y divided by x. And we're going to take that substitution and help us solve for our final result. So u is y over x. So we have the natural log of x is equal to y over x minus 2 natural log of y over x plus 1 plus our constant. And this becomes our solution to the differential equation. So some of these take a lot of steps, but no step was necessarily difficult. It was merely identifying it as homogeneous, making a substitution, and then solving the resulting separable equation. There's another substitution that I want to show you in this video, though. Our second type of substitution is called a Bernoulli substitution. A Bernoulli differential equation is of the form y prime plus p of x y equals q of x times y to the n. And what you might notice with this is it almost is linear in form. The only difference is that y to the n. That's going to promote our strategy with substitution. We're going to let u equal y to the 1 minus n. Taking the derivative of both sides, u's derivative becomes u prime. Y is a function of x, so when we take its derivative, we get 1 minus n times y to the negative n times the derivative of y, which is y prime. What's nice about this substitution is it makes the Bernoulli equation linear. So let's take a look at an example where we can use this substitution to make a linear equation, which we already know how to solve. Let's do xy prime plus y equals x squared y squared. One thing we notice is this is not yet in Bernoulli form because Bernoulli has y prime by itself. So I need to actually divide each term by x. And when I do that, we'll get y prime plus 1 over x times y equals x times y squared. And now it's Bernoulli almost linear, which is what's going to promote me to make my substitution that u is equal to y to the 1 minus, in this case because we have a y squared, 1 minus 2, which is y to the negative 1. Taking the derivative of both sides, u prime is going to be equal to negative y to the negative 2 times the derivative of y, which is y prime. So now we're ready to manipulate our Bernoulli equation to make it into a linear equation. Notice we already have the y prime. What it's missing is the negative y to the negative 2. And so that's what we're going to multiply both sides by. When we do that and distribute through, negative y to the negative 2y prime is u prime. When we distribute onto the second term, a negative times a positive is a negative, 1 over x. And when we multiply by y, we end up with negative y to the negative 1, which is u. Equals, on the right side, we end up with x, actually negative x, don't lose that negative sign. And now we've got that linear equation we know how to solve. Let's get us a little more space to solve it in. And we've got that negative 1 over x. So we're going to integrate negative 1 over x dx, which is negative natural log of x, which is equal to the natural log of x to the negative 1. We're going to multiply by e to that. But when we do e to the natural log of x to the negative 1, that becomes x to the negative 1. So we're going to multiply both sides of the equation by x to the negative 1. And when we do, we know the left side is going to become x to the negative 1 times our independent variable, the derivative of that product. The right side turns out to be a beautiful negative 1. So we can integrate both sides dx, and we get x to the negative 1u is equal to negative x plus our constant. Multiplying both sides by x, and u equals negative x squared plus a constant times x. We're now ready to make our substitution back to y's. We know that u is equal to y to the negative 1. So y to the negative 1 equals negative x squared plus cx. And since y to the negative 1 is just a reciprocal, we can flip both sides over, and we get y is equal to 1 over negative x squared plus a constant times x. And we've now solved our Bernoulli equation by making the substitution that u is equal to y to the 1 minus n. This little trick will always change your Bernoulli equations into a linear equation, which we already know how to solve. All right, now it's your turn to practice with these substitution tricks, substituting to make a homogeneous equation into a separable equation, or substituting to make a Bernoulli equation into a linear equation. Go ahead and practice those, and good luck.